Hi, it's Professor Jones. I'm here to talk about Section 2.1, the basics of functions and their graphs. The objectives are to find the domain and range of a relation, determine whether a relation is a function, determine whether an equation represents a function, evaluate a function, graph functions by plotting points, use the vertical line test to identify functions, obtain information about a function from its graph, identify the domain and range of a function from its graph, identify intercepts from a function's graph. So, let's talk about the definition of a relation. A relation is any set of ordered pairs. The set of all first components of the ordered pairs is called the domain of the relation. The set of all second components is called the range of the relation. So let's look at an example. Here's a relation, a set of 1, 2, 3, 4, 5 ordered pairs. The ordered pairs are grouped together in a parenthesis, separated. The pairs of numbers are separated by commas. The domain consists of the set that has all the first elements in it. So the domain is the set of numbers 0, 10, 20, 30, 40. And those could be in any order. In a set, order doesn't matter. In an ordered pair, order matters. The range is the set that contains the numbers 9.1, 6.7, 10.7, 13.2, 21.2. So, let's define a function. A function is a relation in which there is a correspondence from a first set called the domain to a second set called the range. So far, we've only defined a relation. Every relation has a correspondence from the domain to the range. But this third portion is what distinguishes a function from a general type of relation. So a function has each element in the domain correspond to exactly one element in the range. So this part of the definition is what distinguishes a function from the general garden variety relation. So let's take a look at the relation 1, 2 is the first ordered pair, 3, 4 the second, 6, 5 the third ordered pair, and 8, 5 the fourth ordered pair. So notice every domain element or first component corresponds to exactly one second element or one range element. So yes, this relation is a function. Functions can also be given as equations. If an equation is solved for y, and more than one value of y can be obtained for a given x, then the equation does not define y as a function of x. So let's look at an example. So let's determine whether the equation defines y as a function of x. X squared plus y squared equal 1 is our equation. So let's solve that for y. Our first step would be to subtract x squared from both sides of the equation. That leaves us y squared on the left and 1 minus y squared on the right. Let's use the square root property to solve for y. So y equals plus or minus the square root of 1 minus x squared. So there are many x values. You just need one x value that corresponds to two y's, and the equation does not define y as a function of x. Well, if x is 0, y is not only positive square root of 1, which is positive 1, it's also negative square root of 1, which is negative 1. So if that happens for just one x, this is not a function. The equation does not define y as a function of x. So the plus or minus is the thing that shows that for certain values of x, there are two values of y. For this reason, the equation does not define y as a function of x. Let's take a look at function notation. So this special notation, here our letter that gives the name of our function is f. Beside the letter name of the function is a parenthesis with the variable inside of it. That variable is the independent variable of the function. So you read this f of x or f at x. And keep in mind, it doesn't mean we're multiplying f and x. But instead, f of x represents the value of the function at the number x. So let's look at an example of evaluating a function. First, the function has to be defined. So in our example, f of x is x squared minus 2x plus 7. And we're being asked to evaluate f of negative 5. So that basically tells us in the defined function, replace every x with negative 5. And now we have f of negative 5 equals the square of negative 5 minus 2 times negative 5 plus 7. So the order of operations say first apply the square to negative 5. You'll get 25. Then you're multiplying negative 2 times negative 5 to get positive 10. And then, of course, you're going to add 7. And the result is 42. So f of negative 5 equals 42. So you can also present a function as a graph. So the graph of a function is the graph of its ordered pairs. So if I'm told to graph f of x equal 2x and g of x equal 2x minus 3 in the same rectangular coordinate system, selecting integers for x starting with negative 2 and ending with 2, then that means I'm going to set up a partial table of coordinates for each function. So these functions contain infinitely many ordered pairs. But we're going to use 5 ordered pairs to get the graph. Then we're going to plot those points, those ordered pairs, and connect them. So we're going to use red to graph f of x equal 2x. So we're going to start by making a table. We pick our 5x values, and we replace x with negative 2. So 2 times negative 2 is negative 4. 2 times negative 1 is negative 2. 2 times 0 is 0. When x is 1, we get a y of 2 times 1, which is 2. When x is 2, our y is 2 times 2, which is 4. So let's use blue to represent g of x. And notice when you pick your x, you multiply it by 2, and then you subtract 3. Well, we've already done 2 times x over here. So all we really need to do for these same x values is to subtract 3 from these y values for f of x equal 2x. And we'll have the y values for g of x. So when x is negative 2, our y is negative 4 minus 3, negative 7. When x is negative 1, our y is negative 2 minus 3, which is negative 5. When x is 0, our y is 0 minus 3, which is negative 3. When our x is 1, our y is 2 minus 3, which is negative 1. And when x is 2, our y is 4 minus 3, which is 1. So we have 5 points, or 5 ordered pairs, which we can plot. And the red points are the 5 ordered pairs for f of x. Negative 2, 4. Here x is negative 1, y is negative 2. Here x and y are both 0. Here x is 1, y is 2. Here x is 2, y is 4. So remember, this is a partial table. It only showed 5 ordered pairs for this function, but the function has infinitely many ordered pairs. Every point on this line represents an ordered pair of the function, and it continues on in both directions without end. So if I was writing this by hand, I would have put an arrow on each end of this line. Similarly, we plot negative 2, negative 7 for g. X equal negative 1, y equal negative 5 is a point on G. X equals 0, y equal negative 3. X equal 1, y equal negative 1. X equal 2, y equal 1. So if I connect those 5 points with a line, then that line is indicating that there are infinitely many ordered pairs for this function. Okay, so remember, a function can be presented as a graph, as we see in this example. The vertical line is a test you can use on a graph to see if the graph represents y as a function of x. So if any vertical line intersects a graph at more than one point, the graph does not define y as a function of x. And that's because you would have an x that corresponds to more than one y if the vertical line touches the graph more than once. So let's look at an example. Here's our graph, and we want to use the vertical line test to identify whether or not the graph represents y as a function of x. Well, notice here's a vertical line that touches the graph in more than one place. So no, y is not a function of x on this graph. Well, let's rotate that curve 90 degrees. Notice that any vertical line that intersects this graph will only do so once. So never is there an x that corresponds to more than one y. So this graph does represent a function. Y is a function of x on this graph. Also, we'll want to analyze the graph of a function. Here in this example, you have a graph that represents the x values represent time after infection in years. The y-axis represents the average T-cell count per milliliter of blood. So we want to use the graph to find f of 5. So that basically means x is 5. So I find 5 on the x-axis. I move vertically until I touch the graph. In this case, I have to move up to get to the graph. And now I find out the y that corresponds to where I landed. That y is 400. So f of 5 is 400. Now notice this graph is divided into 3 colors. The red portion of the graph is the asymptomatic stage of the HIV infection. A person who's HIV positive, it looks like it's about 3.5 up to 3.5 years after being infected, has few or no symptoms. From 3.5 years to about 8 years, the person is in the symptomatic stage. Their symptoms begin or get worse. And so that's the blue portion of the graph. Then the green portion of the graph, from 8 to 11 years, is where the person has a clinical diagnosis of AIDS. And notice what's happening to the T cell count, how it's going down once the time progresses. So 5 years after infection, the person is in the symptomatic stage of the illness and has an average T cell count of about 400. Now we're being asked to find the value of x for which f of x is 100. So that means we want to start with y equal to 100, which is midway between the x-axis and y equal 200. And when we see the graph is to our right, so we're going to move to the right until we touch the graph. And we touch the graph when x is 9. So we can see when x is 9, that's when we touch that graph. So f of 9 is 100. So x equals to 9 when f of x is 100. So that basically means 9 years after infection, the average T cell count is all the way down to 100. And this is when the clinical diagnosis of AIDS occurs. All right, let's identify the domain and range from a function's graph. So to find the domain of a function from its graph, look for all the inputs on the x-axis that correspond to points on the graph. To find the range of a function from its graph, look for all the outputs on the y-axis that correspond to points on the graph. So we call x values inputs and y values outputs. So let's look at an example, a couple of examples. Here's our graph. So you can see this blue curve represents our graph. And essentially, we just look at the inputs that correspond to points on the graph. So -2 is the smallest x value for a point on the graph. And notice that if all of these points are bigger than -2, once I move to the right of that point that has the smallest x. And these are all points in the function's domain. X equal +1 is the largest value in the domain. So the domain is the set of all x such that x is between -2 and 1, including -2 and 1. Now let's look at the range. And here's how you would write that as an interval. The square brackets indicate that the -2 and the 1 are included in the domain. Now let's look at the range. So I'm at a point on the graph, and I go over to the y-axis, and I see y equals 0 is my smallest y. Now notice the y's increase from 0 until y is 3. So y equals 3 is my largest y equals 0 is my smallest y, and then all the y's in between are the y's of my range. So the range is all y's between 0 and 3, including 0 and 3. Here's how I write that using interval notation. Notice the square brackets indicate the 0 and 3 are included. Let's do another example of this. There's our graph. First, let's do the domain. Notice that the smallest, actually, when x is 2, this open circle is not a point on the graph, but it's earmarked or identified because immediately to the left of that x value the graph begins. So x equal negative 2 is not part of the domain, but everything, and then let's go to the right most point on the graph where x is 1. So 1 is the largest point on the graph. The x equal 1 is the largest x value that corresponds to a point on the graph. All other x's are smaller than 1 but bigger than negative 2. So the domain is all x's bigger than negative 2, smaller than or equal to 1. And as an interval, I have a parenthesis beside the negative 2 because negative 2 is not in the domain. 1 is in the domain, so there's a bracket beside that. And all points between negative 2 and 1 are in the domain. Now for the range, notice the smallest range value, smallest y value is y equal negative 1. Notice that the y's become larger and larger, but when I get to y equal to 2, that y is not in the range. So the range consists of all y's that are either equal to negative 1 or bigger than negative 1, but smaller than 2. And in interval notation, there's a bracket beside the negative 1, a parenthesis beside 2 because 2 is not in the range. The last thing we want to do is identify intercepts from a function's graph. So to find the x-intercepts, look for the points at which the graph crosses or touches the x-axis. To find the y-intercept, look for the point at which the graph crosses or touches the y-axis. A function can have more than one x-intercept, but a function will have at most one y-intercept. So that means it may have no y-intercepts or one. It can have either no or many x-intercepts. So let's take this function, and the red points are our x-intercepts, the blue point is our y-intercept. So notice to be on the x-axis, y has to be 0. So negative 3, 0 is this x-intercept. Negative 1, 0 is this x-intercept. 2, 0 is this x-intercept. So those red points are our x-intercepts. Now let's find our y-intercept. That's our blue point. So to be on the y-axis, x has to be 0. So notice y is negative 6 and x is 0. And that is our last topic for this section. And hope you found this helpful, and that you'll do well and finish up in 2.1 and go on to section 2.2. Bye-bye.